little flawed.
How's it going?
5 days would be better than
Not good.
Like I got 3.
All right. But I can't say much about the test because I still have someone in the process of taking it. Plus, I have a couple of people who haven't taken it yet. So I will post the key when I can. If you want to come in individually and ask about things, I'm more than happy to do that. All right. So we got some new stuff to cover. So let's talk about section 3.5 of your text, which is what's referred to as the gamma and the chi-squared distributions.
Are these your favorite distributions, Dr. Joe?
Are these my favorite distributions? I wouldn't say any of them are necessarily my favorite ones.
Do you have any favorite distributions?
Not particularly. All I'm saying me. Now, as far as usefulness goes, the chi-squared distribution is exceptionally useful in statistics. In particular, one of the things that you're interested in doing, pardon me, goodness. One of the things that you get interested in doing in statistics is worrying about the variances of distributions. In particular, if you're trying to do any types of hypothesis testing between two different populations, one of the assumptions that you would like to be able to make is that the variances are equal, because it makes the hypothesis test easier to do if the variances are equal. And the chi-squared distribution gives you a way to see if that's a plausible hypothesis or not. So as far as a useful distribution goes, if you're going to go on to take mathematical statistics, you will see the chi-squared distribution pop up again. Okay. And it turns out the chi-squared distribution is a special case of the gamma distribution, so that's why it falls into this particular section. But the chi-squared distribution, and we'll see a little bit in the next chapter why the chi-squared pops up where it does, and how it relates to more general types of distributions, in particular the normal distribution. And then later on, even farther in the semester, we'll talk about why the normal distribution is as important as it is. So if I were to pick a favorite distribution, it'd be the normal one, because if you take sample sizes that are large enough, everything's normal. So I guess that would probably be the favorite one, because that's going to be the one you're going to use the most often. So.
Is there an unimportant distribution?
Is there an unimportant distribution? Probably the ones that are made up that don't necessarily have any applications, or just used to teach the top the concepts. So those would probably be like the ones where they just give you something and say show that it's a PDF, so that it has those properties, or find the constant to make it a PDF. Those kinds of distributions are typically just made up to practice the concepts, so those aren't necessarily important distributions, except for the fact that you're learning the concepts. So as far as the important ones go, the ones that are named are typically important. They have other ones that pop up that we won't spend a lot of time on, but we'll mention that come up in applications. The Weibull distribution, for one, is something that pops up that's good for applications that we'll talk about briefly, but won't have a lot of things to do. But the ones that are named because they actually have some actual use somewhere. So somebody that actually gave time to put a name to it. So anyway, but yes, I would say that they're unimportant ones. Those would be the ones that just are made up and don't have any necessarily aren't necessarily applicable to statistical testing. I mean, that's the whole point of doing all of these things, is that somehow they're modeling some sort of scenario that has to do with probability. So, for example, the exponential distribution is representing something that is increasingly unlikely the farther you go out, right? So if you've got something that you would expect to, like lifetimes, for example, how long something lasts, you would expect that eventually it's going to die off, right? So something like the exponential distribution is good for modeling those kinds of things. From statistical theory and sampling theory, we know that if we take sample sizes that are large enough and look at the means, we know that eventually that's going to be normally distributed. So the normal distribution is good for those scenarios. What else? Chi-squared, like I said, talks about doing variances. So if you're doing modeling of variances things, you're going to be looking at a chi-squared distribution. Those kind of things. So that's why these are important, because people made them up to be able to do some sort of analysis. That's by the way, that's part of Dr. Lee's research, is that she looks for other types of statistical testing that can be done on different things. So if you want actual reasons behind some things, you should talk to Dr. Lee or Dr. Roth, because he knows everything. But
So is the chi-square important and the gamma is less important than the chi-square?
the gamma is, I wouldn't say it's less important, because both the exponential and the chi-squared are special cases of the gamma. So, and it's used to model some other things too. It's just depending on what you're trying to model. It's just the chi-squared one pops up when you're looking at variances. And it's the reason why is because of the way that when you do the square of a normal random variable, that's why the chi-squared pops up. That's where the chi-squared pops up, which is why it's so important. All right, anyway, so let's talk about where these things come from. So we already talked about the exponential distribution coming about from the Poisson process. So one of the things that we really want to emphasize is that the Poisson and the exponential are these inverse ideas of each other, right? If you've got the Poisson, which talks about number of occurrences in a given time period, the exponential that's associated with it talks about the waiting time until the first one occurs. There's that tie together. Even though the Poisson is a discrete random variable and the exponential is a continuous random variable, given a Poisson distribution, there's an exponential distribution tied to it. And given an exponential distribution, there's a Poisson distribution tied to it. They're related. And that was that relationship with the lambda for the Poisson is the reciprocal of the theta for the exponential, right? Those connected those two ideas together. All right, so for the gamma distribution, it's basically the natural extension of the exponential. So let's say that we have, let's let W be the waiting time. Oops, I can spell the waiting time until not the first occurrence, that's exponential, right? But until to make it as general as possible, we'll say the alphth occurrence, because of course we have to use a Greek letter of whatever. The alpha occurrence of whatever, what word do I want to use? I'm just stumbling over the place, over the word. Oh, I was going to say of a Poisson process. Doesn't matter. Remember, Poisson process says that we have these things arriving, if you will, at random times. Two can't happen at the same time. That's what we mean by the Poisson process. What W is doing is it's measuring the time until not the first one occurs, not necessarily the first one occurs. The first one occurs was exponential, right? Waiting time until the first thing occurs, right? This is saying, okay, not the first one, but maybe the 5th one, or the 20th one, or since we're going to do this in general, the 3.6th one, whatever that means. The pith one occurs, okay? We're just generalizing this. That's the idea, okay? So W is counting that waiting time until that alpha one occurs. So let's see if we can get at the CDF again through that idea that we talked about before. if I look at the CDF, remember again by definition, the CDF is the probability that your random variable is less than or equal to a particular value. This is a standard, I'll say trick, but it's not a trick. This is a standard way to try to get the PDF of something that you don't know to start with. We're going to do more of this later in the semester. Start by finding the CDF and then take the derivative to get to the PDF. Okay? All right, so because we don't know in general how the PDF is defined. The PDF is the distribution or the density of what the probability is at any given point. But it's not probabilities at a given point, right? It's density. To figure out probabilities, you actually have to integrate to find probabilities in continuous random variables. Okay? Instead, I know the definition of the CDF, right? I don't necessarily know what the definition of the PDF is for some distribution that I haven't dealt with before. Okay? But I know how a PDF or a CDF is defined. So I can start there and work my way to get to the PDF by taking a derivative at the end. Okay? All right, so this is, W is counting waiting time until the alphth occurrence. Okay? Well, let's attack this like we did with the exponential. That I know that capital W needs to be less than or equal to little w. Let's just say alpha is 3 for argument's sake. Okay? Well, I don't know if the three occurred within the first 5 seconds or within the first 10 days or less than that, because I have that whole interval to work with, right? So instead of trying to figure it out directly, let's go indirectly and look at the complement. So we'll do 1 minus the probability that capital W is greater than little w. Okay, so what that means is that at time little w, we have not seen alpha occurrences, right? Do you agree? Okay, so this means that we have not yet seen alpha occurrences. Now, if alpha is an actual integer, I can do this with the Poisson, correct? So if I haven't seen alpha occurrences, I might have seen none, I might have seen 1, I might have seen 2, and so on up the line, correct? Up until I get to alpha minus 1. So this would look like 1 minus the sum from k equals 0 to alpha minus 1 of our Poisson idea. Well, if I have lambda per unit time, remember again, we can take lambda times the time interval to give us the new mean for that time interval, right? So it would look like lambda times w. If we see lambda per unit time and there's w time increments, right, then we will use lambda w to the k, and then e to the minus lambda w over k factorial. Right? We did this with the exponential, didn't we? Right? Okay. So now we can get to the PDF by differentiating. Right? So if I want to take the derivative here, that's how we get from the CDF to the PDF. We take the derivative. So little f of w will be capital F prime of w. All right, so we need to be able to see if we can figure out what this derivative is. So let's just think about what this would look like written out longhand. Okay? So this would be 1 minus the quantity. I'm going to write it as lambda to the k, w to the k, and then e to the minus lambda w. Except I lost my summation, didn't I? So let me write the summation back in here first and then actually write it out, sorry. I'll just erase it, it's easier. Squeeze that back in here. I only want to write that out to start with because I want to be able to take the derivative. All right. So the first term here will be what? I'm going to plug in 0 for k. This term's going to go away, isn't it? That'll be a 1. The denominator will also go away, right? And I'll just have an e to the minus lambda w there. There's a reason why I'm doing this, by the way. Why I wrote a k? Lambda w. Okay. What will the next term be?
Lambda w, e to the negative lambda w.
Okay, so I'll have a plus lambda w e to the minus lambda w. Right? The next one will be the lambda squared. Right? W squared e to the minus lambda w over 2 factorial. Then we keep going up, lambda cubed, w cubed, e to the minus lambda w over 3 factorial. And keep on going until I get to lambda to the alpha minus 1, w to the alpha minus 1, e to the minus lambda w over alpha minus 1 factorial. All right, that looks ugly, and it's going to look ugly for a minute, but things will get better, I promise. All right. Ignore the first term. If I'm going to differentiate with respect to w, what derivative rule are we going to need to use in each term? Well, yeah, let's use a chain rule for the lambda w part. But yeah, I got to use a product rule, right? Because I got a w and an e to the w, right? So for everyone except for the first one, we're going to end up with 2 terms when we take the derivative, right? And in fact, when I do that, one of them will be positive when I take the derivative of the w part. One of them will end up being negative when I take the derivative of the e part, right? So we're going to get flipping signs as we go through. Okay, so let's see what happens. This should be fun, right? It's calculus, right? All right, so let me write this equal sign a little bit lower. Derivative of the 1 on the outside. Thank you. Wasn't a trick question. Derivative of 1 on the outside is 0. All right. Derivative of e to the minus lambda w. What's going to happen there?
E to negative lambda w times
Negative lambda w.
Yeah, good. Negative lambda will come out in front, right? Because w is our variable, correct? We agree?
Yeah.
All right. All right, so let's do the product rule in the second term. Let's differentiate the w part first. What do you get when you differentiate the w first in the product rule in the second term? Hey, look at that. That one's positive, right? Anything nice is going to happen there? Those are going to cancel out, all right? But of course, I only took the derivative of half of what I needed to take the derivative of, right? I took the derivative of the first times the second. I also need to do the first times the derivative of the second. What do you get when you take the first times the derivative of the second? Okay. So far, so good? Let's do the next one. What do you get when you take the derivative of the second one, or the third term, I guess I should say?
Positive lambda squared w e to the negative lambda w.
Okay. Get positive, he said lambda squared w e to the minus lambda w. And the reason for that is what happens? When I take the derivative of the w squared, the 2 comes down and cancels with this one, right? The front one here, correct? Okay. All right. And notice now these 2 terms will cancel, won't they? What's the derivative of the second part in this one then?
Negative lambda cubed w squared e to the negative lambda.
Okay. Over 2 factorial. Right? Now let's do the third one. Or fourth one, I guess. This one here. What do we get there?
Positive lambda cubed w squared e to the negative lambda w over 2 factorial.
Okay. And then where do we have 2 factorial on bottom? What happens there?
The 3 dot everything W cancels out.
Good. When I take the derivative of the w cubed, the 3 comes down and cancels off the first one off the factorial, right? Okay. So I'm left with 2 factorial on the bottom. And notice that's going to cancel with the previous one, right? The next one's going to be what? Yeah, lambda to the 4th. Okay. Over 3 factorial, right? But we can probably guess what the next one's going to be, right? The next term is going to have a w to the 4th and a 4 factorial. When you differentiate that, the 4 that comes down in front will cancel with the 4 that's in the factorial, so you'll end up with lambda to the 4th w cubed e to the minus lambda w over over 3 factorial. And those will cancel, right? We agree? Okay? And then the next one will be continuing what it is. So we agree that all of these terms here in the middle are going to cancel, right? What's going to be the only thing that survives? The very, very last one when we differentiate the e to the power, right? Because notice that every time we differentiate the w to a power, it's canceling with the previous one, right? When we differentiated the w, it canceled with the e to the minus lambda w in the previous one, right? When we canceled with when we took the derivative of the w squared, it canceled with the w term. When we took the derivative of the w cubed, it canceled with the w squared term, right? So the only thing that survives is the very, very last term when you take the derivative of the e to the minus lambda w. And this won't be a plus, this will actually end up being a minus inside here. When I take the derivative of the e to the minus lambda w, we get lambda to the alpha, w to the alpha minus 1, e to the minus lambda w over alpha minus 1 factorial. No canceling in that factorial because we're differentiating e to the power. Absolutely everything else cancels out. And notice I want this term to be a minus, this last term to be a minus, because what's sitting out in front of the parentheses? A minus, right? And our PDFs always have to be positive. So I get lambda to the alpha, w to the alpha minus 1, e to the minus lambda w over alpha minus 1 factorial. All right, so if alpha is an integer, this gets you to what a PDF should look like for the gamma distribution. Lambda is the mean of the underlying Poisson process. Alpha is the number of occurrences. Now again, to get to this point for this particular problem, we had to assume that alpha was an integer, right? Because we went through the Poisson pieces to get that, right? To get the terms in our sum. Okay? But this gives you an idea of what the PDF should look like. So what we're going to concentrate on now, is kind of one of my favorite things to do, is looking at how do we generalize this. In particular, I don't have any issues up here if alpha is not an integer, right? I can do numbers to fractional exponents. Fractional exponents mean do roots. You can do numbers to irrational exponents. You just approximate it with a bunch of rational exponents until you are satisfied with the answer is, right? There's no issues changing these to fractional pieces because I can do fractional powers, right? What we don't see usually is fractional factorials, right? Okay, so let's see how we get to a fractional factorial because you can actually do that. Okay, so that's what we're going to do right now. It's fun stuff. I think it's fun. This kind of stuff is why I got interested in math. All right. So to that end, we're going to define what's referred to as the gamma function. All right, so the gamma function we use, well, they use a T in the book. I'm going to use alpha because that's what we're talking about anyway. So alpha is the input, gamma is just the name of the function. So gamma of alpha is going to be the following. It's going to be the integral from 0 to infinity of x to the alpha minus 1 e to the minus x dx. Kind of ugly, right? But it's not too bad. In particular, let me ask you this question before we do some properties with this. What is gamma of 1?
1.
Why? Because you read the book. Okay? I agree. Gamma of 1 is 1, but let's see why. If I put 1 in here, what's the exponent on the x? 0, right? So this just becomes integral from 0 to infinity of e to the minus x dx. Antiderivative of e to the minus x is negative e to the negative x, right? When we put in 0 here, what do we get? Well, you get 1, right? When it's negative in front, I always like to put it in the lower than the upper because that actually gives me the actual positives and negatives, because it's basically when we're with the negative in front, reverse flips your limits of integration. So put in 0, I get 1. We go to infinity, e to the minus infinity goes to 0, right? So this just turns out to be 1. So gamma of 1 really is 1, right? We agree? Okay. All right. Now, doing this for a general alpha is, more difficult, but we can get some properties. Okay? In particular, let's say we were going to try to do this for a general alpha, whatever that happened to be. Assuming that alpha is not 1, if I'm going to integrate this by hand, what technique am I going to have to use? Okay, I'm going to have to use it by parts, right? Because I got a product of two things, and that's not a U substitution. Right? If it's a product of two things and it's not just a simple U substitution, probably going to have to use integration by parts to integrate it. And if I have an exponential term in my integral, should I ever let the exponential term be U in your integration by parts? No. Remember, when you do integration by parts, the whole point of doing integration by parts is to make the integral simpler. The way you make the integral simpler typically is by differentiation, right? If I differentiate e to a power, what always pops back up? E to that power. Did that make the integral get simpler? No. Okay? So there's no reason ever to make your u equal to e to the x, or e to a power. That's just not good form at all for integration by parts. There's no sense in it, right? Remember, integration by parts is a technique to help you simplify the integral to see what the antiderivative. All of your techniques of integration are just algebra rearrangements to help you see things. Okay? You don't ever actually have to use any of the methods that you ever learned. If you're smart enough to figure out how to rearrange that algebraically, you can get the answer. Okay? It's just a way to help you see what the answer is supposed to be. Okay? All right. So in this particular case, if we go to this again, taking this integral and coming down here, I would let my u be x to the alpha minus 1, and my dv be e to the minus x dx. Right? What would du be then?
Alpha minus 1.
We're differentiating. X to the alpha minus 2, right? Just power rule, right? Antiderivative of e to the minus x, you just told me about 30 seconds ago. Yeah, good. So now if we apply our integration by parts formula, what is this going to equal?
Negative x alpha minus 1 times e to the x.
Okay. That's evaluated from 0 to infinity, right? That's our u times our v. And then Why is it plus?
E is negative.
Okay, so remember the integration by parts formula is integration by parts formula. It sounded it's an unfortunate slip of the tongue. It's a very, very interesting way to integrate. All right, integration by parts formula, enunciation is important, is uv minus the integral of v du, right? Okay, minus a minus makes a plus. Integral from 0 to infinity. I can pop out move this plus sign over a little bit. I can pop out the the alpha minus 1, and inside we're left with x to the alpha minus 2, e to the minus x dx. All right. We'll worry about the integral in a minute. Okay. Let's look at this piece, the first piece, the non-integral part, that first part. What happens when you plug in 0?
The x is -1. Negative x.
I'm putting 0 in for x. I get 0, right? I get a 0 here, aren't I? Okay. And then if I put in infinity, this part's going to go to 0 as well, correct? Okay. So this goes to 0. This whole entire term goes away. As long as your alpha is bigger than 1, that certainly works. Okay. Turns out it works if it's negative as well, but I'll worry about that in a minute. Even if your alpha minus 1 is less than 0, that still is going to end up going to 0. Okay? All right, so anyway, maybe actually you may need your alpha to be between -1 and 0. Think about that. Anyway, this is going to go into 0. This part over here, though, looks like what we're trying to integrate, doesn't it? What's been changed? There's an alpha minus 1 in front, and this power on the x went down by 1, didn't it? Now remember that when we did gamma of alpha, I got alpha minus 1 as my exponent, right? That was how it was defined, correct? So how can I rewrite this integral in terms of the gamma function?
Gamma of alpha minus.
Go back up here again. This exponent is 1 less, right? So it should be gamma of alpha minus 1, right? So this is going to be alpha minus 1, times gamma of alpha minus 1. So we get this property of your gamma function. Why is this property important? Well, number one, this gives you, if all of you have done sequences. You've probably seen recursively defined sequences, right? Where future terms are in terms of previous terms, right? One of your famous recursively defined sequences is your Fibonacci sequence, right? Let the first term be 1, let the second term be 1, and then every other term is the sum of the previous two. So the third term would be 2, the fourth one would be 3, the fifth one would be 5, and so on up the line, right? You've seen recursively defined sequences. Later terms are defined in terms of previous ones. That's what we have here, right? If I want to know gamma of alpha, I need to know gamma of alpha minus 1, which would be in terms of gamma of alpha minus 2. Which would be in terms of gamma of alpha minus 3, and so on up the line, right? So in fact, say as an example here, say I ask you to find gamma of, gamma of 5. Well, according to this formula we just found, what's alpha? What's playing the role of alpha here? 5. So I plug in 5. So what's that going to equal according to the formula? 4 times gamma of 4, right? What's gamma of 4? What will be?
3 times gamma of 3.
Good. And what's gamma of 3 then? And what's gamma of 2? Good. 1 times gamma of 1, and didn't we already say what gamma of 1 is? 1, right? So this is just 4 factorial, isn't it? So gamma of 5 is 4 factorial. So in general, if alpha is an integer, and it's just a fancy looking Z, which stands for the integers. Okay. If alpha is an integer, gamma of alpha is simply alpha minus 1 factorial. Because if it's an integer, you'll pop the alpha minus 1 out. Or if alpha is an integer, you'll pop an alpha minus 1 gamma of alpha minus 1. When you replace the gamma of alpha minus 1, an alpha minus 2 pops out. When you replace the gamma of alpha minus 2, an alpha minus 3 pops out until you get all the way down to 1. So you have alpha minus 1 times alpha minus 2 times alpha minus 3 all the way down to 1. So you get alpha minus 1 factorial. Now again, this particular function is defined for alphas other than 1. But it agrees with the factorial function on the integers. So in a way, this gamma function is a generalized factorial. Okay. All right. Now, one of the ones that does pop up from time to time is is basically 1/2 factorial, if you will. So to get 1/2 factorial, or what gamma of 1/2 would be, you have to do some fancy work, which I'll do next time. It's more fun. It'll take me longer than 10 minutes to do it. But you can talk about doing things like what's 1/2 factorial using this particular function. And it turns out that 1/2 factorial is a square root of pi. It's kind of fun. Okay. We'll show how that works. I promise, we'll show how that works. It's kind of fun. I think it's fun. Right?
What's the square root of pi?
What's the square root of pi? I don't know. That's what calculator's for. Somewhere between 1 and 2.
Isn't the square root of pi over 2?
Square root of pi over 2? Square root of pi.
1.7724.
Yeah, it is. It's the square root of pi over 2. The 1/2 factorial is 0.886229. Then you multiply that by 2 and you get square root.
We'll have to see about that. Anyway, square root of pi pops out of it. Maybe there is a factor that I'm off on. It's possible. I'll look. We'll have to see what the actual answer is. I'm not pi over 2. Square root. Dividing the square root of pi by 2? Is that what you're saying? Okay. It's not what I remember it to be, but we'll do it next. Like I said, we're going to do it next time anyway. So we'll see what it is. Anyway, all right, so what's the point of this particular gamma function? Why did I mention it? So notice that in our PDF, what appears in the denominator? When we came up with that PDF before, what appeared in the denominator? That alpha minus 1 factorial, right? But we said that alpha had to be an integer for that to work. But now we've got a function that behaves like the factorial function, okay? So what we say is that the gamma distribution, the PDF of the gamma distribution is, we'll say f of x. On top, we'll have an x to the alpha minus 1. And instead of having a lambda from the Poisson process, we're going to invert it like we do for the exponential and make it a 1 over theta. So in your exponent for your e, you'll have an e to the minus x over theta. And then the denominator will have a theta to the, usually we write it the other way around, gamma of alpha. That's taking the place of the alpha minus 1 factorial, and a theta to the alpha. Again, we think of this theta as the waiting time parameter, right? Remember for exponential, the theta was your mean waiting time, right? Right? Okay. So this was we thought that theta as being the mean waiting time for one occurrence in the Poisson process, so it was 1 over lambda. That was how we got it. Right? So all I'm doing here is that lambda that we saw before that was up in the top, we just moved it down to the denominator with a theta. Okay. This alpha minus 1 that was in your denominator is now being replaced by the gamma of alpha. Okay? You can check that this satisfies your properties of being a PDF pretty quickly. And you can also figure out the mean and the variance of this distribution pretty quickly, and its moment generating function. So let's do mean. Say I want to do expected value of this. If I do the expected value, I would do x times the PDF, right? That's how we do expected value, isn't it? And then, oops, forgot my dx. So what would this do to this power here? Yeah, make it x to the alpha, right? Okay. And then I would still need to do this by parts like we did before, correct? If we do that integration, if I wanted to figure out what the mean is, I would have to do integration by parts. So you would let your u equal x to the alpha. Du then would be what?
Alpha x to the alpha minus 1.
Okay. Your dv, again, would be e to the minus x, and we've done this at least 3 times today. We get a minus e to the minus x, right? We agree? Okay. So it's uv, so we would have minus x to the alpha e to the minus x, evaluated from 0 to infinity. And then minus the integral of v du, but I got a minus in front again. So I get plus, I'm going to pop the alpha out front. Integral from 0 to, and then I've got these other constants. Oops, I did forget my other constants, didn't I? I still have gamma of alpha, theta to the alpha. I have x to the alpha minus 1, e to the minus x over gamma of alpha, theta to the alpha, dx. I forgot to write down the gamma of alpha and the theta to the alpha because, well, I'm an idiot, but they're constants. They don't have any x's, right? So they weren't having a lot of effect on the integral. I can just move them, right? Okay. Let's look at that first term again. What do you get when you put in 0 for x? 0. And as x goes to infinity, what happens to that term? Goes to 0, right? So again, this term goes bye-bye. Right? So yeah, it's great that you wrote it down, right? Because it goes away again. Let's look at the second term. In particular, let's look at the integrand of the second term. Does it look familiar? Yes, it does. In fact, that's exactly the PDF of the gamma distribution, right? So we're integrating a PDF over its entire support. What does that integral have to be? 1 times alpha, right? Oh, I'm forgetting a term somewhere.
Yeah, exactly.
Oh, I know what I forgot. Crap. I forgot my thetas. My bad. I got excited. When I anti-differentiate, not only do I get a negative here, what else pops out?
One negative theta.
A negative theta, right? That's what I forgot. Sorry about that. So a theta goes here, right? Technically, there's a theta here, too. I'm not going to worry about simplifying. Sorry about that. I forgot my theta. I need that theta. Now I have a PDF for a gamma distribution that goes to 1, so this expected value becomes alpha theta. All right, let's tie this to what we've already talked about. Why would I ever want to do that? Let's tie this to what I've already talked about. We talked about the exponential distribution before the test, right? That was waiting time until first occurrence, correct? What was his expected value? Theta, right? This is now waiting time until alpha occurrence. Well, we expect theta until the first one. If there were 2 of them waiting for the second occurrence, you would expect 2 theta. If there were 3 of them, you would expect 3 theta. In general, you expect alpha theta. The exponential distribution really is just an extension, a special case of the gamma distribution. The gamma distribution is an extension. So what would you think the variance is? Alpha theta squared, right? It's going to be the same thing. The alpha just goes along with it. And then the moment generating function turns out to be 1 minus theta t to the alpha, which is not a huge surprise. Think about why this isn't a huge surprise. Okay, the 1 over 1 minus t is your moment generating function for the exponential, right? So that part's not a surprise. Why would the alpha be up in the exponent? Remember, how do we find the moments? What do we do to the function? Derivative, right? So when I take the first derivative, what's going to come down in front? An alpha, right? And a theta will pop out by your chain rule, so you get an alpha and a theta, right? If you do it again, you'll get an alpha squared and a theta squared, but you're going to end up subtracting off an alpha squared and a theta squared when you do your minus mean squared for your second one. But it's not a huge surprise that there's an alpha here, because I need to bring it down in front when I take the derivative to get the mean. So those are the important pieces for your gamma distribution. All right. So next time, we'll talk about doing some problems with these, because we did a lot of derivation stuff today, I know. But it's important to know where these things come from. We'll also get into chi-squared, which is just a special case of this. We'll do all that next time. We'll do some problems too. Enjoy. We'll see you later. Is that good enough for time, Gray?